Okay, so it's my pleasure to introduce today's speaker, Christophe Breuil from CNRS and Université Paris-Saclay. Christophe did his thesis under Jean-Marc Fontaine, and he has won several distinctions for his work in number theory. For example, he taught the Cours Pecot, he won the Prix Gaston Julia and the Grand Prix Jacques Herbrand. He also won a silver medal from the CNRS and he spoke at the International Congress of Mathematics. And today he's going to talk about the local Langlands program and characteristic P.
Thank you. Thank you very much, Giovanni, for the invitation. Thank you for being there. So, sorry, I'm trying to, there's a window. Yeah, just if you can reduce the window because there's, I don't really, thank you. Okay, great. Thank you very much. Yeah, so I'm going to talk about the local Langlands program and characteristic P, and the talk is not intended to specialists. This is a colloquium talk, right? So there will be 5 parts, if time permits. So the first part will be GL1. This is all the results. This is the introductory part. Then I will switch quite quickly to GLN. Of course, I'm not going to be technical, of course, this would be impossible. And then I switch to characteristic P, fields of characteristic P, as you will see, which is the main subject of my talk. So, case of GL1. Throughout the talk, I'll have some elementary notation. So P will be a prime number. Okay. ZP will be the ring of p-adic integers. Okay, so you take an integer, you can expand it in base P, as you know. Well, so the p-adic integers would just extend this expansion formally to plus infinity. And this defines a ring, addition map, and so on, multiplication. This is there's a natural p-adic topology on it. 2 integers are very close if the difference is divisible by a very high power of p. Okay, this is called p-adic topology, and this makes the ring a compact ring. And now, if you invert p and define qp zp inverted p, this is called the field of p-adic numbers. So now this is a field. Everything except 0 is invertible, and this is a locally compact field. It's not anymore compact, but every point has a compact neighborhood. In this talk, I'll need K, a finite extension of QP. So this is a field containing QP, and which is finite dimensional as a QP vector space. So for instance, you can have QP itself. You can take any root of P, you can add any root of P to QP, or you can add the square root of -1, which you can write as QP x mod x squared plus 1. And you see there is this assumption P congruent to 3 mod 4. Because if P is congruent to 1 mod 4, the square root of -1 is already in QP, so you don't need to add it. And finally, I need the ring of integers of K, which is denoted OK. So OK is to K what ZP is to QP, but the formal definition is as follows. You take all monic polynomials with coefficient in ZP of X, and you take all these roots, which are in K. Monic polynomial, so the leading coefficient is 1. And this is, again, a compact ring. Okay, so you can define these things. And then I have well, I'm going to define something called the reciprocity map, but I need a second slice of notation, and that will be all, at least for the moment. So QP bar will be the algebraic closure of QP, which just you take all finite extension of QP and yet you put them together. You take all roots of all polynomials with allowing QP. This gives an algebraic closure of QP. And then I need the Galois group of QP bar over K. So this is the field automorphisms of QP bar fixing K point by point. Okay, so bijection from QP bar to QP bar, which respect multiplication, addition, and which fix elements of K. And this is a non-commutative group, a big group. This is actually, so this is called the Galois group of QP bar over K. And this is a profinite, hence compact group. And the reason is it is profinite because you can write it as projective limit of all the finite Galois group for all the finite Galois extension of K. Okay, and of course each Galois L over K is a finite group. So this is why it is profinite, and any profinite group is compact. And finally, I think yes, I need the largest abelian quotient of this group. So if you take any group, if you mod out by the subgroup of commutators, so elements generated by, the subgroup generated by elements like G, H, G-1, H-1, this is a subgroup of commutators. then you get the largest abelian quotient of this group. So here we do this. So except we take the closure of the commutators because there's a topology issue, but that's okay. And this is again a profinite group, which you can endow with the quotient topology. I mean, this is not okay. And here's the first theorem. So this theorem, I mean, I put the name of Hasse. I'm not exactly sure who did it first. Maybe there are people who know here better than I. Certainly, let's go back to the first half of the 20th century in Germany, let's say, mostly. So you have two groups here. You have K cross, meaning K minus 0, the invertible element of K, okay, which is just the same thing as GL1 of K on the left-hand side. And on the right-hand side, you've got the biggest abelian quotient of this Galois group. So these two groups are sort of very different. The one is just on K, and the other one concerns all extensions of K and the automorphisms you can have with these extensions. So it's sort of living in different worlds. But still, it turns out there's an injection of topological groups with dense image of K cross inside the abelianization of Galois QP bar over K. So which means since it has, this is an injection, it has dense image. This means roughly these are the same groups, roughly, okay? I mean, you could take the profinite completion of K cross and get really an isomorphism. So this is quite strange. And this says, in fact, just if you want to impress your friends, you just say, this is Langlands correspondence for GL1, right just from there, and which you can state as follows. If you take any commutative field and any one-dimensional representation of Galois QP bar over K, so since over E, so since it's one-dimensional, it factors through the abelian quotient, okay, because GL1 of E is commutative. And then it corresponds to a representation of GL1 over K, which turns out to be also one-dimensional here. And the proof is straightforward. You take your representation of Galois QP bar over K. It factors through the abelian quotient, trivially, and then you just compose with the embedding of GL1K inside Galois QP bar over K of the above theorem. And you get your one-dimensional representation of GL1 of K, okay? So that's just Langlands correspondence for GL1 of K. And now I'm gonna switch quite quickly to GLN of K. And so let me start with some preliminary first. Let me fix E a commutative field and G a topological group. Then a representation of G on E vector space is called smooth, or we could also say locally constant, if any vector of V is fixed by an open subgroup of G. This means the action is continuous on V for the discrete topology on V, if you like, and the topology you have on your topological groups. So maybe it helps to fix ideas to mention that open subgroups of GL and K are just those which contain conjugate of finite index subgroup of GLN OK. For instance, conjugate of GLN OK. For instance, conjugate of GLN ZP if you are with GLN QP and so on. So, I mean, open subgroups have to be understood as a sort of big subgroups by opposition to closed subgroup, which would be much smaller. Open subgroup contain big neighborhoods. So the neighborhoods being these H, for instance, GLN OK. That's for GLN K. And for Galois, the open subgroup are just the subgroup Galois QP bar over L, for L a finite extension of K. So those elements which not only fix K point by point, but also fix a finite extension of L, the element of a finite extension of L. And so you have as many as you have a finite extension of L, okay? And maybe the remark that I already said, that smooth representation is the same thing as the continuous representation where you put the discrete topology on V. So I think I can right now state theorem 2. So that's local Langlands correspondence, but of course I state it in a very vague way because, I mean, if you not especially in the local Langlands correspondence is a huge industry which have been keeping busy thousands of people for several decades, so that you can. So of course it's quite hard to, but still you have the statement. Okay, so if you start with any continuous n-dimensional representation of Galois QP bar over K, which I will take here over C so n-dimensional C vector space, with its natural topology of C, transcendental topology, then to such a representation corresponds a smooth, irreducible, infinite dimensional representation of GLNK over C, meaning an infinite dimensional C vector space equipped with a smooth action of GLNK, and which is irreducible, meaning the only subspaces stable under the action are either the whole space itself or zero, nothing in between. This is irreducibility. So of course the whole statement is in this word, corresponds, which I cannot describe here, but I can give a few examples. So let me make a few remarks. First, about the transcendental topology of C that is used here, which may, well, it may look a bit strange. In fact, you can prove that any continuous n-dimensional representation of GLN of Galois QP bar over K over C is actually locally constant, smooth. So because the topology of the Galois group doesn't mix with the transcendental topology of C. So the argument is to prove that, if you're curious, is that there's an open neighborhood of 1 in GLNC equipped with its transcendental topology that doesn't contain any subgroup apart from 1 itself. So if you use this, you can easily see that if you are continuous, you must be locally constant. And so in particular, it factors. So you take the inverse image of identity. The inverse image of identity is open because it is continuous for the discrete topology, because it's smooth, and hence factors through a finite quotient of Galois QP bar over K. So Galois L of K, because Galois QP bar over A is open, as I said. And so hence it's semi-simple in that case. Okay, direct sum of irreducible. Okay, and maybe I should mention that the most interesting irreducible representation of GLNK over C are those corresponding to n-dimensional irreducible representations of Galois, and they are called supercuspidal. Okay, I put a condition of irreducibility on the GLN side, but not on the Galois side. On the Galois side, I take anything that occurs of dimension n. And they are important because using supercuspidal representations of GLMK for smaller m, you can build all irreducible representation of GLNK. Yeah, and I should mention that characters of GL1K are considered as supercuspidal representation of GL1K, in case you wonder. There's trivial case, but okay. Let me give you one example, which we keep throughout this talk. Which is the most elementary example of this correspondence. So you pick n characters of the Galois group, so smooth, so continuous, so smooth characters from Galois QP bar over K to C cross, and you consider the direct sum. So this is an n-dimensional representation of Galois QP bar over K. And so the representation corresponding to this Galois representation is the following. So this is maybe the most technical part of the talk. So forget about, this is just notation. So the definition is here. So this is a space of functions. I mean, it is infinite dimensional. So usually such representation are given by spaces of functions. So you take functions from GLNK to C, which are locally constant, and such that they satisfy a certain functional equation, which is given here. So here B of K is a Borel, is the upper triangular matrices. Well, maybe it is given below. Yeah, B of K is the upper triangular matrices. Here B1, Bn is the torus part of the diagonal part of your upper triangular matrix. And the functional equation is given here. F of Bg is, so you've got a character of the torus, K1 of B, something here that I'm going to explain, n-1, K2 of B, and so on, times F of G in C. This is called a functional equation, and you take all these functions satisfying this functional equation. So these two bar is a p-adic norm. So Bi is a p-adic norm of Bi. You have the definition here. Maybe the only thing to remember for the talk is that it lands into the rational numbers of the form 1 over p to the z. Okay, and finally, yes, you need a group action, of course, since you need a representation of GL and K. So you take a function, and you have to explain how the group acts on this function. So G prime of F is another function, so I define it for any G, and this says F of G prime. You just translate on the right. We say right translation. And you see this is still in the space because you multiply on the right, but the functional equation is on the left. So this function still satisfies this function equation. You are careful about that. And such representations are called principal series. So that's the terminology is due to the analog of this in the Archimedean, I mean, for the reals and so on, where they are the main representation. I mean, for the p-adic theory, this is a little bit strange. They're not so much principal, in fact, but they're called principal series. And they don't depend on the order of the ki. That's one important feature, maybe the first non-trivial statement here. You see the representation itself is a direct sum of the ki. So you can make any permutation you like on the ki. So that has to be the same on the GLN side, because it's, of course, it's a correspondence between isomorphism classes. But if you look at the definition of the function itself, or the representation, it does depend on the order of the ki. I mean, if you change the order of the ki, you get other functions. But it turns out there are intertwinings between the two principal series, and this is a non-trivial fact. And for these for these intertwinings to be there, you need to twist by these p-adic norms. Otherwise, it wouldn't be isomorphic when you change the order of the ki. Okay? Yes. Now, yeah. So that's all I want to say about local Langlands correspondence of a C. Now, I'm going to talk about characteristic L. So if you're interested in analysis, this must be strange to go through characteristic L. But if you're interested in number theory, we do this all the time. We spend our time reducing things model, because usually either there are new phenomena model, or it's easier model, or whatever. I mean, so we spend our time reducing models. So it was very natural to see what happens of this correspondence when we work over finite fields, or at least algebraic closures of FL for any prime number. Okay, so this was actually started by Marie-France Vigneras in the 80s, middle of the 80s, so a long time ago, and revisited by Emerton and Helm around 2010. And in fact, if you assume L distinct from P, I mean, I'm a bit vague in my statement, so I can basically recopy the statement. It still holds, except there's one small difference, which I will explain. So if you take any continuous n-dimensional representation of Galois p bar over k over FL bar, so here I put the discrete topology of FL bar because there's no other topology available, because it's a finite field, basically. So it's again smooth, like previously, but there's nothing to prove. It's just definition. Then, well, it corresponds again to a smooth infinite dimensional representation of GLNK over some FL bar vector space, except that this time it's not necessarily irreducible. It's finite length. There's a finite number of irreducible constituents, but most of the time it is irreducible. So let me give one example. So I chose one example to show you in which case you may have reducibility, but this is not very important for the rest of the talk, I guess. Maybe what is more important is this first line. Why do we assume L different P? Well, here's one reason. You take the p-adic norm. The p-adic norm has values in 1 over p to the d, and you see, since P is different from L, you can reduce it model, and you land into FL bar. And so you reduce mod L the p-adic norms. And so, in fact, this norms here extends by continuity to Galois p bar over k via the map reciprocity, which recall that reciprocity was going from k cross to Galois q p bar over k made abelian, and it has dense image. Okay, so the norm is a character of Galois p bar over k, so it factors through the abelian quotient, and it actually extends by is a character on k cross as it is defined. You see here it's k cross. It extends uniquely by continuity to the Galois group, which was not the case of the p-adic norm over C, in case you wonder. And using this representation, you get the case where on the GL2 side, for instance, you have something which is non-split. So you take the Galois representation 1 plus norm minus 1, and then corresponds to this representation, actually non-split extension of 1 by a certain space of functions, which is called the Steinberg. This is not very important for this talk. I just wanted to mention the one difference, essentially, between the mod L case and the mod and the characteristic 0 case. And the proofs, so the proofs are, I mean, of course, different than the proofs of a C, but it's not a revolution. I mean, it's not a revolution. Okay. Okay, and maybe I should mention that actually on the Galois side, we know more semi-simple now. I mean, the case of a C was a little bit specific. Okay, so I guess I'm done with the characteristic L different from P, and it's very natural. Sorry, yeah. I mean, before I switch to characteristic P, there are a certain number of remarks, important remarks that I would like to make on this correspondence. The first is that actually, so I didn't explain what, apart from giving one example, but the representation of GLNK associated to a two-dimensional, well, n-dimensional, so there's a typo here, it's n-dimensional, sorry, I should have, representation of Galois QP bar over K satisfies multiple properties which actually characterize it. And the simplest is about the action of the center. So you see K cross embeds into GLN of K, X is sent to X on diagonal, and it acts on the vector space by multiplication by the character of K cross corresponding to the determinant of the Galois representation composed with the reciprocity map. So the n-dimensional representation, there's a determinant. It gives you a character from the Galois group to the F C bar or FL bar cross. You compose this with K cross, and this gives you the action of all element K cross on the GLNK side. Of course, now you have all the action of all the other elements in GLNK, which is far. But I mean, this is one of the properties, one of the many properties. Another important remark is that the local Langlands correspondence, I mean, which I define sort of vaguely, purely locally, is actually not a pure construction of I mean, it actually sort of pre-existed in the sense that there are towers of algebraic varieties called Shimoa varieties. You can take the étale cohomology, if you know what it is. So these are cohomology groups where you have both an action of Galois and of GLNK, which commute. And actually, you can decompose this cohomology according to the action of these groups, and you find exactly a representation of Galois tensor the corresponding representation of GLN. So it really matches sort of in the cohomology, and in some sense, the étale cohomology, I don't know, historically was developed independently of the local Langlands program. So you see, it's sort of really, it really works. I mean, and it appears in real life. Yeah, but this is called local global compatibility. Local global compatibility, because the construction of étale cohomology of Fiorama varieties is some global construction. You do not have, you don't need a local field and so on. I mean, and it's one of the deepest facts of this correspondence. Okay, it naturally occurs on certain spaces, and there exist even today many generalizations. I mean, as I told you, it's a huge industry. So you can replace GLNK by the K point of any reductive group, symplectic group, orthogonal group. You can categorify the correspondence, meaning it's no more a bijection between isomorphism classes, but it becomes an equivalence of categories, and even between suitable derived or infinity categories, if you like to play with that. And you can also consider metaplectic groups, which are not algebraic groups, but they're still a version of the correspondent for that, and so on. So as you see, okay, now I switch to characteristic P. And I'll start with a very simple group, GL2QP, which is the most simple case. So from now on, all representation will be over FP bar vector spaces, L equals P, okay? And the first theorem very much looks like the previous one. So I go on with, so they started, I mean, the first people who had a glimpse at characteristic P are Bartel and Livney in the beginning of the 90s. Then I revisited and generalized what they did in more than 20,000 years ago, and then Colmez a little bit after, again generalized. And you can, I mean, again, you can state, you can give a statement which is very similar to the one for L different from P from the outside. So to a continuous two-dimensional representation of Galois QP bar over QP over FP bar, so with a discrete topology, correspond to smooth finite lengths, again, infinite dimensional representation of GL2QP over FP bar. But now the proofs are completely different from the case L different from P or C. And I want to give you one example which shows one how it can be different. The first, the p-adic norm. It's, you cannot reduce it, I mean, you cannot reduce it mod P. 1 over P, mod P gives 1 over 0, which doesn't exist, okay? So it is in fact replaced by something which is called the mod P cyclotomic character. which is defined as follows. You take K cross, you take the norm map to QP cross. So the norm is a determinant. K is a QP vector space. Just take the determinant. This lands in QP cross. Then you send P to 1. This lands in ZP cross. And then you reduce mod P, and then you are in FP cross, Z mod PZ, and then you embed this into the arbitrary closure. And this is the mod P cyclotomic character. This is actually what replaces the p-adic norm. And it again extends by continuity to Galois QP bar over K, just as in the case L different from P with the p-adic reduction mod L, the p-adic norm. Okay. And so let me consider the representation K1 plus K2, the case of principal series over C. So except now we are of dimension 2, as I said. And I mean, I need to assume a small genericity condition on the characters. So K1, K2 minus 1 are distinct from omega plus or minus 1. Otherwise it's a little bit different. I don't want to go into, I mean. Then what corresponds to this is direct sum of two principal series. So these principal series here, I define exactly as the principal series were defined. I mean, if I go back, maybe I can quickly go back. Yeah. Okay, let me quickly go back to the case. Yeah. So you just replace everywhere GLN of K by GL2 QP, and you replace this by, I mean, by the characters Chi1 and of B1, little omega of B1, and so on. And you get, this is the same definition with the same action and so on. So you get infinite dimensional FP bar vector spaces, but this time they are no more isomorphic. They depend on the order of the Ki. And so we can take the two of them. So of course, if you take two of them, it doesn't depend anymore on the order of the Ki. So you may object that this is artificial to do this. You have two principal series, they're not isomorphic anymore, you just take the two of them. But in fact, it does occur in cohomology groups. This is, and so it's not at all artificial. And this is related to an old phenomena that Serre had already remarked years before, which is called the companion mod P modular forms. But these are two companion manifestation of two companion modular forms, in case you have heard of this. Anyway, so that's one big difference. It's of course no more irreducible, but I mean you have two principal series. Okay, maybe another example, because it's not too complicated to state. Let me take sigma, which is an irreducible finite dimensional representation of GL2 ZP QP cross. Maybe you can forget the QP cross. The interesting thing is GL2 ZP here over FP bar. For instance, you can take the trivial representation for sigma. And then I'm going to define another functional space, another kind of induction. This time I do not induce from the Borel, but I induce from GL2 ZP QP cross, GL2 QP. So the eigenfunctions from GL2 QP to sigma, which have compact support modulo QP cross. This is the meaning of the CN. This is compact induction, compact support modulo QP cross, and which satisfy the same kind of functional equation. F of Kg is K applied to F of G, with remembering that F of G lands into sigma, and so K acts on F of G via this finite dimensional representation, sigma of GL2 ZP QP cross, okay? And GL2 QP again acts by right translation on functions, okay? So this is called a compact induction, okay? So it looks nice. The only problem that it is of infinite length. It's a smooth representation. Yeah, the representation, I didn't say it, but with these functional equations, they are automatically locally constant. And so this is a smooth representation of GL2 QP over FP bar of infinite length. But you can prove that there's a canonical GL2 QP equivalent endomorphism, which we call T, sometimes U, depends on what you prefer, between these two compact inductions. And yeah, well, the last sentence, you can forget it if you... So there's a canonical endomorphism, and you can consider the quotient of this compact induction by the image of this endomorphism. It's not subjective, okay? So you can take the quotient by its image. It's non-zero, and it's actually an irreducible so-called supercuspidal representation of GL2 QP over FP bar, meaning it doesn't occur from principal series or subquotient of principal series. And they actually correspond to the two-dimensional irreducible representation of Galois QP bar over QP over FP bar that I didn't describe. But you can, that's the supercuspidal representation in characteristic P, except we call them super singular. for some historical reasons. The terminology is due to Barton and Livney, not me. And maybe let me finish with the case of GL2QP with a couple of remarks. The first is that the smooth representation, I mean, you could do the same in characteristic 0 over C or FL bar. And maybe you think that this will give you supercuspidal representations. Actually, no. Once L is different from P or you are in characteristic 0, they are isomorphic to principal series. And if you want to describe supercuspidal representation, it's a completely different description. It turns out that mod P, in that case, it's pretty easy, okay? And the correspondence of the previous theorem is actually realized on the étale H1 with FP bar coefficient, and this is an important theorem of Emerton, around 2010. So again, these two principal series that you saw are naturally occur on cohomology, including the supersingular representation when on the Galois side it's irreducible, and so on. Everything matched the cohomology. Okay, so that was GL2QP. Now, in the first half of 2000s, there was hope that the previous results would extend without too many problems from GL2QP to GLNK, because in the case of a model different from P or over C, you do not see the proofs are the same whether you work with GL2K or GL2QP. There's no difference at all in the proofs. So we were expecting the same thing up to small difficulties, extra difficulties. Fortunately, we're still here right now. You see, I stay hope, and I'm possibly optimistic. So the hope is that we still have some naive statement. We could maybe have some naive statement like this to any continuous n-dimensional representation of P bar over K with a discrete topology, maybe correspond to smooth finite length infinite dimensional representation of G9K over FP bar. But I want to explain why, what happened. And this took some time and why it's still open. You will see. Essentially, it all comes down to supersingular representations. Multiple issues appeared when you trying to get out of GL2QP. The first thing is that if K is different from QP and sigma is an irreducible representation of GL2OK over FP bar, you can do exactly what I did previously. Take the compact induction of sigma and divide my quotient out by the image of C. But this time it is no more irreducible, it has infinite lengths. Bad news, okay? So if you're confident, you can go forward and use Zorn's lemma. Zorn's lemma tells you it has irreducible quotients. So abstract, this is abstract nonsense, okay? And so this quotient must be supersingular. This is easy to prove. These quotients cannot occur from principal series. So they are by definition supersingular quotients. Okay, so we have supersingular quotients, but the problem is that if you want to describe them, they are defined by unknown infinitely many equations, meaning you add to this quotient T infinitely many other equations which are not known. So this is a result of Schrey and Wu, you see over the past decade. So second bad news, not only this is of infinite lengths, but the quotients are basically, you cannot describe them explicitly. Okay, so let me go on. Paradoxically, in fact, there is many such irreducible quotients, even though we cannot describe them. We can prove this. This is joint work of myself with Pascunas, following previous work of Pascunas. We prove actually that many more such quotient than two-dimensional representation of Galois P bar over K. Remember that for GL2QP, they were exactly the same number. The supersingular representation matches the irreducible two-dimensional representation. Here, we cannot describe them, and there's a huge number of them. There's two bad news. It's not over. And yeah, one keeps finding new ones over the years. Last year, I mean, you can improve the combinatorics and prove new supersingular representation, not isomorphic to the one of my paper with Pascunas, or I mean, and of course, I mean, it's not over. So you don't know where it's going to stop. Okay. So I mean, then you can ask whether they have a Galois interpretation. Personally, it's not clear to me. I mean, I've been struggling with this supersingular representation for years. And I would not, it is not clear to me if all of them have a Galois interpretation. Maybe you can find statements, sort of more sophisticated statements, which you, by the way, borrow from either the mod L of the complex theory. Except here, you have to be very careful when you mod P. So maybe, I don't know if all of them have a Galois interpretation. Certainly not in a naive statement, like I said, naive correspondence. Okay, it's still not over. You may object that, okay, but let's look at the reducible case. Because in the reducible case for GL2QP, we had two characters. We only had principal series, no supersingular representation. So maybe this case, at least, we can deal with it. Well, no. In that case, you have the two principal series, as I will explain at the end of my talk. They are indeed still there, but they're not alone. There's a supersingular friend here also, and you don't understand it. So there's no way you can escape supersingular representations if you are looking at cohomology, at least, if you're looking at cohomology. And for GLNK n bigger than 3, it's even worse. I mean, it's even worse. Okay, a priori, we expect that more super, I mean, we know less, but we expect the worst. Sorry. And we almost know nothing on the supersingulars. So my experience over the past 20 years is that the supersingular representations are very elusive. So as soon as you think you're about to get one, sort of manages to escape. And this is, I mean, really in every aspect. You can attack this problem from geometric side, representation theory side, number theory side, combinatoric side, lots of way. Each time there's a supersingular representation that you suspect is sort of lurking in the dark, you bump into something impossible to prove so far. So this is quite systematic. Okay, but the situation is not desperate as it looks like. I would like to finish with optimistic, more optimistic results. And tell you about some recent results of GL2QP, and of course the proofs will be very different from GL2QP because of this of these issues. So first, there are even results for GLN of K. The following theorem, a nice result of Florian Herzig, which from Toronto, not so far from here, which he obtained in 2010. In fact, you can use the supersingular representation to build all smooth, irreducible, admissible representation, like for supercuspidal representations. Except I added a word here, admissible, that I will explain right after this theorem. But otherwise, they play the role of supercuspidal representations, except we do not understand them. So this was proved by Florian Herzig. And there's a second theorem, which was proved 10 years later by Herzig, Koziol, and Viniraj, well, which is rather somehow bad news because it tells you that there exists smooth, irreducible, admissible supersingular representation for all n and k. They do exist, not just for GL2. Okay, they are there. But of course, their proof. I mean, well, I'll say a word about their proof. First, the word admissible. Admissible means, so it's an extra condition on a smooth representation. It means the invariant vectors under any open subgroup of GL and K, for instance, GL and OK, actually are finite dimensional. I mean, if you take any smooth representation, this is not the case in general, but there are some which are nicer than the rest, which do behave sort of well for compact open subgroups. The invariant vectors are finite dimensional. This is the finiteness condition called admissibility, and it is actually automatic over C or FL bar. So all the representations of this talk are admissible. But it's not automatic over FP bar, which is why I have to mention it. I mean, if you finite length over C or L, you're automatically admissible, so no need to mention it. Okay, the proof of Herzig, Koziol, and Viniraj on the existence of supersingular representations is very much global. It uses automorphic forms. Because we do not have the local theory, and it doesn't say anything more on supersingular representation than just the fact that they exist. They use some very global space of automorphic representation. They reduce it mod P and prove that at some point something cannot be a principal series, something like that. But they do it very generally, so it's I mean, it's a nice reason. Okay, now I would like to finish with so sorry, what time is it? Ah, my God, I went maybe too fast. Sorry. I didn't know. Okay, maybe I can slow down now. I mean, you can ask questions if you want to. So I would like to say some results for GL2K for K different from P. Okay, so what do we do now? So you can still do many things, but what I did is that you see, since the representation is satisfied on cohomology groups, we can look at cohomology groups and try to understand what's going on there. And I hope to find something like a correspondence there. This is quite natural. In all cases, model different from P over the C. This is always satisfied in cohomology groups. For GL2QP, this is satisfied in cohomology groups. So let's look at cohomology for GL2K. We have towers of Shimura curves. We take cohomology with some eta H1 with FP bar coefficients, and you can do this. But this has a cost, a big cost. If the methods, these methods, the method you can use to study this are powerful methods, they're called global methods, but they are also blind. Because they are powerful, they do let the local aspects behind them. And a priori, you do not know that what you find is only depends on the fixed Galois representation Galois P over K. It might depend on lots of other stuff that is used, like the Shimura curve themselves, the global setting, the geometric setting, and so on. Yeah. But still, there's no, if you want to, well, I mean, this is still an important question because the cohomology is important. And so we could prove recently the following theorem. So with my co-authors, Florian Herzig, Yon-Chan Hu, Stefano Mora, and Benjamin Schren. So that the theorem is a reunification of two sort of two kinds of result. One obtained, first kind obtained in 2021, and the second obtained this year, in fact. But there are a few assumptions now, which are important assumptions. We assume K is unramified extension of QP. So, for instance, OK mod P is a field. I assume P is big enough, in particular, bigger than the degree of the field K over QP, dimension of K over QP. And I also assume, right now, this is what is written, that the underlying two-dimensional representation of Galois QP over K is semi-simple. So either irreducible or direct sum of two characters. And in that case, at least we can prove that the associated representations of GL2K on the eta H1 are of finite lengths. A finite number of constituents, and the length is bounded by 1 plus the degree dimension of K over QP. So, by the way, you see that if K equals QP, you find 2. This is the case of the two principal series. So, and in the reducible case, there was 1. So this is why it's only a bound. And you can also prove that they are irreducible and supersingular if and only if the Galois representation is irreducible. So, I mean, if you look at cohomology, things at least gives you finite length things, which have sort of nice properties. Irreducibility when you expect it, and finite length. So it looks not so bad, but it's very, I mean, these results are not quite painful to get. I'll say a word in a minute. Let me give you the example of the semi-simple example of K1 plus K2 again. So as I said previously, what we find in the cohomology is the two previous principal series, exactly as for GL2 QP. But now in the middle, there's some extra, there's pi in the middle that is there on the cohomology, and it is a representation of lengths smaller or equal that the dimension of K over QP minus 1. So when K equals QP, this gives 0, so it's not there, but it's there as soon as K is different from QP. And all its irreducible constituents are supersingular. This we know. So it's purely in the world of supersingular, the supersingular world that we do not understand. So, and so in particular, if dimension, if you are in a quadratic situation, then it's irreducible. It's an irreducible supersingular which is there with these two principal series, and there's no way you can avoid it. Actually, we conjecture that in that case, K1 plus K2, pi should be itself semi-simple and of length exactly dimension of K minus 1. So it would be the direct sum of this number of supersingular representations, which should be distinct. If it is semi-simple, it's not difficult to see that it should be multiplicity free, at least in generic cases, maybe. But we do not know if pi only depends on K1 and K2. So you see the principal series here obviously only depend on K1 and K2. This thing occurs on cohomology, it's of finite length, even irreducible if dimension in quadratic case, but it's a global stuff. So it depends, may depend on the totally real field, on the Shimura variety, on the quaternion algebra, on the prime to V level. I mean, lots of stuff you need, and so far, I mean, whatever you can compute on pi, because of course we can compute a lot, will always be local. but it has been impossible so far to prove that it is local. Let me mention quickly another result due to Yunchan Hu and Aoran Wang in 2020, but actually they use the method of previous theorem. Anyway, they looked at the non-split case, and in the non-split case for the quadratic situation, you find that you have something which is undecomposable, but the pi you have is in the middle. So you have a sub-representation is a principal series. You have then a non-split extension in your pi, and a non-split extension the other principal series. Okay, but of course we do not know if pi is the same as in the semi-simple case. Again, because we do not know. I mean, the construction is global, so certainly it depends on the non-split extension, but it could also, again, I mean, I don't know, depend in some fancy way on a totally real field length. So you see, this is the kind of thing you have to pay when you use the powerful global methods. They're very powerful because it's impossible to get this via local methods. But then the price is that it's a little bit blind. Okay. So what are the techniques of proof? So here I'm not going to be technical at all. So the proof is mainly global, as I said, and it has very technical parts, but there are two main global ingredients. The first is the last technology in the Taylor-Wasserstein patching method. So we push them as far as we can and as we need. And the second actually is we use the self-duality of the étal H1 of Shimura curves. And this is an important thing which only holds for GL2, which means that if we want to extend our result to GL3, it's no more self-dual. So this means that it's not going to be possible to extend the proofs without serious, non-trivial new ideas. But at least with these two ingredients and also, I mean, this is of course not enough. You need the heavy local computations. Unfortunately, both on the Galois part, we need to compute some subtle potentially crystalline deformation rings, and on the GL2K side, and the computation are not the same. Yeah, and combining all this, we can prove this finite length theorem. So maybe let me, since I have time, yeah, here it is. That on the cohomology, you have things of finite lengths, which are irreducible if and only if the representation is irreducible, and otherwise which have this form when it's reducible. I think that's finished. Okay, thank you. I actually was afraid to go, but maybe I went. So you may ask questions if you have any.
Yeah, I was saying this.
Yeah. So can you say a little bit more about when you said that they were global constructions of this correspondence? So you're realizing the correspondence in the cohomology.
Yes.
What are the Shimura varieties exactly that intervene? So you have a choice, I guess.
It's yeah.
You have
so
one.
But then I can use the board. So I mean, you take F over Q. So let me all the thing we need is a totally real number field, meaning all its embedding into C actually lands into R. Then you need a D over F, which is a quaternion algebra, which you assume is split at only one infinite place, and possibly at some other places, but at the infinite place, only one infinite place. We want a curve. So, I mean,
so it's always H1.
Well, you could maybe, this is an open question now. I mean, for instance, one possible direction of research would be to try to extend this proof to HD of some Hilbert-Blumenthal stuff. Presumably, this is doable using recent results of Tamiyazo, Karayani, and so on, something like that. But you won't get more than what we have for H1. You will just get that this is again like here, this is again finite length, and so on. You won't know whether the representations are the same as for Shimura curves, but at least you can maybe do things. But I assume this because at first it's easier to deal with H1 and curves, right? You do not have torsion and so on. It's not over. We need place V dividing P in F, where D is split. Okay. So this is another choice. And we need finally, we have we have the Shimura, sorry, we have the adelic quaternion algebras. So That's the finite adels. And if I take them outside of V, I need to fix some maximal compact open subgroup. Open, and then the representation is essentially something like this. No, this is not over. You also fix lots of things. You also fix a global rho bar from Galois, so F bar over F to GL2 of FP bar that you assume is modular. I mean, comes from some reduction mod P of some Galois representation associated to some Hilbert modular forms. And then you consider the inductive the Hom, I mean, Galois F bar over F of rho bar inductive limits over compact subgroup at V of H1 et al. There's Shimura curve UV of F bar FP bar. Okay, and yeah, and this is expected to be a finite length. The representation of GL2 of the completion of F at V. So this depends on F, on D, on V, because it could be that you have a same local field for a different place. It depends on UV, and of course it depends on rho bar also. All this is expected finally more or less to only depend on rho bar restricted to Galois FP bar over FV, and not on all the rest. So you see, it's lots of choices. So that's why it's non-trivial.
So do you believe that there might be some purely local gadget defined over K and not over these auxiliary Fs that would somehow
sorry, say it again.
Do you believe there's some purely local object whose cohomology which would be defined over the local field K?
So you can so that's you can look at the covariates of the Drinfeld space, which are purely local. So this is some work of Dospinescu, Colmes, and so on. And look at what happens mod P, and what you find is of infinite length. So it's not the same thing. This is local now, but is of infinite length. It's not admissible, and so they checked that. They were expecting to find something local or finite length, and but no, it's of infinite length. If you want something of finite length, the only place so far is the global H1, but you do not know it is local. So and so possibly it's not. But so yeah, I mean, if you compute, everything you find is local. So it's very puzzling, in fact. So yeah, I do not know any other geometric object purely local which would give you representation of GL2K in a natural way. I mean, so far. I mean, you may, yeah.
Do you see a parallel between your story and what happens for GL1, where first for classical theory, local classical theory, the first proofs were global, and then there were these local
That's
proofs.
true.
Later there was
that's true.
By Lubin Tate.
Yeah. Well, I hope maybe this is what will happen one day. We find a way to, but so far we don't know how to do this. And we don't know how to get rid of these computations and so on. The proofs of the theorem is, I would say, 40% conceptual, 60% computations. And there's no way so far to avoid the computations if you want to prove finite length and all the properties we have. Yeah. No, there's no. If Drinfeld, the covering local had, I would have mentioned it, of course. I mean, I would, but no, it doesn't. It gives you presumably something like. I mean, I don't know exactly what they have, but I suspect something. You see, I mean, so the problem, of course, is a supersingular case because you also get the principal series and so on. But for the supersingular, you probably have something like this, T, and maybe a few finite number of equations. But we know this is not admissible in infinite length because you need infinitely many equations. So I think they probably have something like that, but I'm not sure they can compute what these equations are. But they know that it's a finitely presented. So they know that there's only finitely many equations.
Can you say something about how the self-duality of H1 is used?
Yeah. So basically, we have this. If you take this pi, so I mean, we need. So let me call this pi for simplicity. And so what I'm going to state needs some technical assumptions, some genericity assumptions, and so on. Some multiplicity one. I mean, you need to take UV big enough and so on. Okay, so let me ignore that. But you have this following auto-duality statement that so I1 is a priori, meaning this matrix is congruent to 1 star 0, 1 mod P in GL2, okay. And I think, yeah, Z1 is the center of I1. I mean, that's just that's not very important. But anyway, so this pi actually dual.
So, can you use the other black?
Sorry. Sorry. Okay. Yeah, I was not. Yeah, maybe I can. So you have that pi dual is isomorphic to x 2k 2p. So k is fv, is the completion fv of my stuff, as an f I1 over Z1 the pi dual f I1 over Z1. This is some sort of Auslander dual auto-duality. You have this. So here, this is the representation of GL2 by a paper of Jan Koolhazer. Yeah, this is called duality in natural characteristics. It's Jan Koolhazer. So this is the auto-duality, and we use this a lot in the proofs, finite lengths and so on. You know lots of things when you about this. You know this is pure of the same codimension and so on, because the strings are Auslander regular and so on. We use all this. So this statement is really related to H2, to H1 and GL2. If you are with GL3 and so on, this is not going to be true. You have, I mean, you can do this, but if you do this, you'll get another representation, which is also interesting. But presumably, if you want to extend the proof, I don't know whether so far we are not there yet. There are other issues before. Yeah, so we use this.
We have no more questions. Let's thank Christophe again for the next talk.
Thank you.